Hello, Assalamu alaikum. Can you hear me, Sarah? Reba, can you hear me?
Yes, sir. Walaikum salam.
Shall we're gonna start. We're gonna we the the main aim for this class is to just revise mass spectroscopy and nuclear magnetic resonance, and hopefully we're gonna do questions on this. Uh, तो पहले ना ये just quickly having a look at mass spectroscopy. Okay, what was mass spectroscopy? What happened? Mass spectroscopy was that you took a molecule, you ionized the molecule, and once the molecule was ionized, what you did was you would pass it through a magnetic field, and it's going to get deflected by the magnetic field. Okay, just 1 second, the board is hanging up. Acha, theek hai. So the particles would get deflected by the magnetic field, and you would get all sorts of deflections. If the particle is light, it's going to be deflected more. If it's heavy, it's going to be deflected less. And there were two types of particles that would be formed. One of them was the molecular ion, which in this case would be CH3 Cl plus 1, or the particle could break up into pieces, which would be its fragments. For example, you could get a fragment of CH3, you could get a fragment of Cl plus 1, you could get a fragment of CH2 plus 1. Okay, all sorts of fragments could be formed. So those were your fragments. So there were three things that you had to look out for when you were talking about mass spectroscopy. You had the molecular ion peaks, which were the M peaks, and I said these were your M peaks. And the M peak would have different. There would be different M peaks depending on the isotope that's being used. For example, CH3Cl plus 1 could have two different masses. And the reason it's going to have two different masses is because there are two types of Cls. One is 35 and the other one is Cl37. And the probability ratio is that the chances of getting Cl35 is 75%, and the chances of getting Cl37 is 25%. So uski wajah se what would happen is that the heaviest particles, the M peaks, there would be two different types of M peaks, and you're going to call them the M peak and the M plus 2 peak. Basically, the mass is going to have a difference of 2 because CH3Cl, the mass of this particle could either be CH12 plus 3, that's 15, 15 plus 35, that is 50. So if you're using Cl35, the mass of the particle would be 50. If you're using Cl37, if the molecule contains Cl37, the mass of this particle would come out to be 52, which is why there's a difference of 2. There's an M peak and there's an M plus 2 peak. This one is 50. This one has a mass of 50. It's a lighter. I'm going to write the mass as well. It's a lighter particle. 52 is slightly heavy, and the reason you're getting 52 is that the isotope is Cl37. So there are going to be two different types of molecular ions, M and M plus 2. And the ratio in which they are going to be detected is 75% and 25%, which is 3:1. So you're going to have a so you're going to have a mass to charge ratio, and over here the M peak and the M plus 2 peak, the relative abundance of the two peaks would be in 3:1. The chances of getting the M peak would be 3 times higher compared to the chances of getting the M plus 2 peak. Mainly because the chances of getting Cl37, that's higher. The chance of getting Cl37 is 35 is higher. The chance of getting Cl37 is lower. So that's the first thing. And there were certain rules. So I'm going to write down all the rules. The first one was that if the molecule contains 1 Cl, TK, which we just did, uh, because of that 1 Cl, you're going to get M and M plus 2 peaks, and the ratio of those peaks would be 3:1. TK, Sara, is this clear? Everyone else, is this clear?
Yes,
Mariam, is this clear? Mariam, is this clear? Anam, Sara?
जी sir.
yes, sir.
Just 1 second. And the other rule was that if the molecule contains 2 Cl, then because of those 2 Cls, the presence of 2 Cls, you're going to get 3 different molecular end peaks. You're going to get an M peak, you're going to get an M plus 2 peak, and you're going to get an M plus 4 peak as well. Okay, so the molecular ion is going to have 3 different masses. And I'm going to just do this on the same thing. Okay, agar if this molecule, okay, let me just change the molecule. So if our molecule had a formula of CH2Cl2, the molecular ion is going to be CH2Cl2 plus 1. And it's going to have the heaviest masses. There would be 3 different heaviest masses. M plus 2, and you would have M plus 4 as well. So you're going to have M plus 4 as well. The M peak would be when both of the Cls are 35. Assalamu alaikum. So both of the Cls are 35. So it's going to be 35, 35. That's going to give you 84. If one of the Cls is 37, that gives you 86. So there's going to be a difference of 2. And if both Cls are 37, the mass of the particle is going to be 88. And the probabilities, if you go into probabilities, the probability for getting this was 9/16. The probability of getting 86 was 6/16. And the probability of getting 88 was 1/16. And you don't need to know how you calculate those probabilities. Actually, you need to have some idea of how those probabilities are calculated. When do you get 88? When both Cls are 37, which means that both Cls are 37. That's going to be the chance of getting Cl37 is 1/4. The chances of getting the other one as Cl37 is also 1/4. So if you multiply the two probabilities, it's going to become 1/16. When you get 9/16, okay, both Cls are 35. So what's the probability of getting Cl35? That's 3/4. What's the chance of getting the other one is 35 as well? That's 3/4 as well, and that's why you get 9/16. So, anyways, these are the probabilities that you have to remember. So, getting 2 Cls, the relative abundance of these 3 types of molecular ion is going to be 9:6:1. So, you have to remember this. And you have to remember the BRs as well. I'm not going to go into details about BR. So getting one BR also has the same issue. Okay, there are 2 types of BRs. There is BR 79 and there is BR having a mass of 81. And both of them, they have equal probability. That's 1:1, which is basically 1/2. The probability is 1/2, and the probability of getting the other is also 1/2. So it's a 50-50% chance of getting either of them. So if a molecule contains 1 BR, the molecular ion is going to have 2 different masses. The 2 different masses are going to be, there's going to be a heavier one which has 81 in it. So 81 plus 15, that's going to be 96. And the other one would be 94 if one of them is 79. 79 plus 14. Let me correct this. 15 plus 81 is 96. This is 79 plus 15, that's 94. So there's going to be an M peak, a peak due to a lighter molecular ion, and there's going to be an M plus 2 peak, a peak due to a heavier molecular ion because the isotopes are different. So इस case में you're going to get an M peak and an M plus 2 peak, but both of them are going to have equal probability. तो दोनों particles equal amount में detect होंगे क्योंकि chances equal हैं. You have equal chances of getting BR79 and BR81. And if you have two BRs, so you can use the same probabilities and उसको extend कर लो जैसा CL का किया था. So getting two BRs, you're going to get an M plus 4 peak. So there's going to be an M peak, there's going to be an M plus 2 peak, and there's going to be an M plus 4 peak as well. And the chances are it's going to be 1:2:1. Okay, so getting the M plus 2 peak would have a higher chance. M plus 4 and M peak would have lesser chances. Okay, is this clear or do you want to explain this further?
जी सर.
बताओ.
ठीक है? अच्छा उससे आगे what's the other thing about this? You have to remember all of this. Then there's another scenario which you have to remember, that is what if the molecule contains one Br and one Cl? Okay, without going into a lot of probabilities, if the molecule contains one Br and one Cl, so how would the molecular ion peaks look like? Okay, for example, if there's a molecule and that molecule is CH2 with one Br and there's one Cl. So this molecule is going to have three different masses. It's going to have an M peak, it's going to have an M plus 2 peak, and it's going to have an M plus 4 peak. Why would it have three different masses? Because either it's Br79 and Cl35, so the mass would be lighter, or it's going to be Br37 and Cl is Br is 79 and Cl is 35. So the mass would be greater by 2, or both of them would be the heavier isotopes. So it's going to be Cl37 and Br81, the mass would increase by 4. So you would have three different particles, and without going into the probabilities, you have to remember that the probability ratio would be 3:4:1. So this entire thing, okay, let me circle this. This entire thing has to be remembered. So apart from this, you can also figure out the number of carbon atoms using a formula. The number of carbon atoms can be obtained because carbon has, the mass of the molecular ion is also going to change because of carbon. Carbon has two isotopes. The more abundant one is the carbon-12, which is 99.8%. The less known one is 1.1%. That's carbon-13. So the number of carbon atoms can be found out by using the same probabilities, and it's a simple formula that you have to remember without going into details. You just have to remember the formula. Okay, because of the carbon isotope, the mass increases by 1. Like if you use carbon-13, the mass of the molecular ion would increase by 1. So there's a simple formula which is that it's 100 over 1.1 divided by into M plus 1 over M peak. Using this formula, you can figure out the number of carbon atoms. और फिर इसमें last जो चीज है कि remember in mass spectroscopy you're dealing with masses. You don't get any idea about the structure of the molecule. The structure of the molecule can be you get an idea of the structure of the molecule by looking at the fragments. So the fragments provide you with information about the structure of the molecule. You're able to identify the smaller pieces. For example, if you look at the first molecule, By just looking at the molecular ion peak, you just get 88. Okay, you don't know what are the atoms in it. You have no idea how the atoms are connected to it. How is the structure arranged? You only get the idea of the mass. But if you look at the fragments, you would get a fragment of 35. That would give you a pretty good idea that there's a chlorine in it. You would get a fragment of, let's say, 15. Uh, you will get an idea that it's probably a CH3. So by just looking at the fragment, the tinier pieces, you can figure out which elements are part of the molecule and which structures are part of the molecule. I mean, if you're getting 14, a particle that has a mass of 14, that would give you an idea that it's probably CH2. Uh, so the fragments, by looking at the individual fragments, you can figure out what the tiny pieces are, and that would give you an idea of this bigger piece. What's this bigger molecular ion? Anyways, we're going to move to NMR, which we wanted to study. Remember, this is all the information that you need from the mass spectrum. तो NMR पे आ जाते हैं. Now, NMR is what's the concept of NMR? In NMR, whenever you have odd number of nucleons, the nucleus or the nucleons are not going to be paired, which is why there's going to be a net magnetic dipole. Whenever you have even number of nucleons, the tiny magnetic fields of the nucleons are going to be paired and they're going to cancel each other out. Like one would be upward spin, the other one would be downward spin, and they're going to cancel each other out. But when you have an odd number of nucleons, the nucleons would not be paired, and hydrogen is one example. That a hydrogen atom, its nucleus contains only one proton. So the proton is going to have a very specific magnetic field, and that magnetic dipole would be pointing in a certain direction. So the hydrogen nucleus would be acting as a tiny magnet. Now, when it's acting as a tiny magnet, organic molecules, they have lots of hydrogen atoms. So let's say we have this molecule, a carboxylic acid. So यहाँ पे ना there is all these hydrogens, and this is a carboxylic acid molecule. And what you do is you place it in an you place it in an external magnetic field. So there are powerful magnets placed around it. This one is the North Pole. This one is the South Pole. Now, before it was placed in this powerful magnetic field, all these hydrogen atoms, they had their tiny magnetic fields pointing in random directions. Okay, so think of them as tiny magnets. The North Poles pointing in completely random directions. But once they are placed in this powerful external magnetic field, what's going to happen is that all of them are going to get aligned with the external magnetic field. Okay, so think of tiny magnets in a very powerful external magnetic field. Think of a compass needle, and all of them, they would get aligned with the external magnetic field. So सारे के सारे ना, they would start to point in the same direction. And remember, carbon or oxygen, they don't have a magnetic field because they have even number of nucleons, and their magnetic fields, they get cancelled out in the nucleus. So this is known as the aligned spin. And that's the low energy state.
Sir, so is the ligand spin when they're all aligned?
Can you repeat your question?
Sir, is the ligand spin when they're all aligned, all the dipoles?
Yeah, I didn't get the spin part. I'll just explain one thing. That a net magnetic dipole and spin, it means the same thing. I mean, it's not the literal spin. When you talk about spin, you're basically talking about the magnetic field. So it's not the literal meaning of the word spin. It just means magnetic field. So I mean, this
Oh,
hydrogen
okay.
proton
Yeah.
has a spin that's pointing in this direction, which basically means, in
Okay.
simple words, it has a magnetic field that's pointing in this direction. Mariam, is this clear?
Yeah.
तो spin पहले भी थी, magnetic field पहले भी exist करी थी, but it wasn't aligned. I mean, they were just, I mean, you can think of compass needles, all of them just pointing in random directions if there is no external magnetic field. As soon as there is an external magnetic field, all of them are going to get aligned with that external magnetic field, and that's your aligned spin.
Oh, sir, sorry. I think I was reading it incorrectly. I thought that said aligand. Okay.
Acha, nahi,
Aligned. Okay, sir.
aligned. Acha, and then what you do is you give all these hydrogen protons energy. You make them energetic. You make them energetic by providing them with radio frequencies. And they're going to absorb those radio frequencies. And if they absorb those radio frequencies, just a second. एक सेकेंड, ये बोर्ड हैंग हो गया. तो यहाँ पे करो. So when they become energetic, they go into opposing spin. So they're going to go into opposing spin, which is the high energy state. So the ones that you see over here, they would start. The hydrogen protons are going to gain energy, and they could now oppose the external magnetic field. They're going to become energetic. And there are only two energy states that actually exist. So there's this aligned spin and there's this opposing spin. Okay, so all of them they start going into opposing spin, and there's an energy gap that exists between the two states. That's known as delta E, and energy that's needed to go into opposing spin. Like if a hydrogen proton is at the low energy state, it would have to gain a certain amount of energy uh, to go into opposing spin. It has to gain a very specific amount of energy to oppose the external magnetic field. Now, to gain that energy, it would have to absorb a certain frequency, and energy is proportional to frequency. So it's going to absorb a very specific frequency. So the hydrogen protons are not going to absorb any random frequency. Like if you give them radio frequencies, they're not going to absorb any random frequency. They're not going to absorb energy from any random frequency. They're always going to be absorbing a very specific frequency. So if a very large amount of energy is needed, they would absorb a higher frequency. If a very low amount of energy is needed to go into opposing spin, they would absorb a lower frequency. ठीक है, ये बात clear? Is this clear?
Ji, sir.
अच्छा, फिर moving on, what does delta E depend on? I mean, what's the ये जो energy gap है दोनों states के अंदर, aligned spin and opposing spin. ठीक है, to go into opposing spin, they have to absorb energy. What does delta E depend on? Uh, so it depends on two things. One of them is the external magnetic field. So if you have a very powerful external magnetic field, for example, in this case you have a very powerful external magnetic field. मैं increase कर देता हूँ उसकी strength. ठीक है, so there are more magnetic field lines now. So it's going to become a lot harder to go into opposing state. तो ये जो delta E होगा ना, that would be much bigger. कि यहाँ से ना aligned spin से opposing spin में जाना, that's going to become very hard. So it depends on the external magnetic field. So a greater external magnetic field as a greater external field, uh, it would make it more difficult to go into opposing spin. And you would need more energy for that. And since delta E is proportional to frequency, a higher frequency is going to be absorbed. ठीक है, तो वो जो absorption frequency होगी, which is now going to be known as the resonant frequency, that's going to change. कि अगर जितनी powerful external magnetic field होगी, उतना मुश्किल होगा resonate करना. ठीक है, so that's factor number one. Is this clear? Sara, is this clear? Maneem, clear? Sakib?
Yes, sir.
जी sir.
Yes, sir.
I said then the other point. I said this doesn't really give you much of an information क्योंकि external magnetic field जो है वो तो आपके control में ना. You can increase the size of the magnets and the resonant frequency would become higher. It's going to change क्योंकि मुश्किल हो जाएगा resonate करना. The second factor is, which is the more important factor, that's the chemical environment. So that's the chemical environment, or that's the, in simple words, that's how the hydrogen proton is bonded in the molecule. So the hydrogen proton could be bonded in a lot of ways. So here's your tiny hydrogen proton. Here's a close-up of that hydrogen proton, and let's assume that that the hydrogen proton is aligned with the external magnetic field. And here's the powerful external magnetic field that's around it. So there's this powerful external magnetic field, and the hydrogen proton is aligned with it. Now the thing is that the hydrogen proton isn't just an isolated proton. It's actually surrounded and bonded with different things. Especially there's an electron. A hydrogen atom always has one electron around it. So there's an electron that is kind of shielding it. So think of an electron cloud that's completely covering it, and that's shielding the hydrogen proton. Because of that, what's going to happen is that the external magnetic field is going to act as a barrier. The electron is going to act as a barrier, and the external magnetic field would get deflected by the electron. Okay, so the electron would be kind of shielding the would be shielding the hydrogen proton. So if the electron density around the hydrogen atom is very high, the hydrogen nucleus in the middle is not really going to experience a lot of magnetic field, and it would be very easy for it to actually go into opposing state. So for it, it's going to be very easy to go into opposing state because it's not experiencing a lot of magnetic field in the first place. Because all the magnetic field lines, the external magnetic fields are getting deflected. But if that electron is not there, let's say there's an H plus 1 ion and that electron has been removed by some other atom. Now, the magnetic field experienced by the hydrogen proton is going to be a lot greater because they're not going to be deflected. So all the magnetic field, external magnetic field lines, they would be passing through it. And the hydrogen proton would be very strongly aligned, and it would be very difficult for it to go into opposing spin. So the point is that the hydrogen proton is surrounded by different atoms. It's bonded in different ways. If it's bonded to a very electronegative element, the electronegative element is going to pull the electron away from it, and the proton is going to be exposed. So if the proton is less shielded, so it depends on what it is bonded to. So if the proton is less shielded, it would experience a greater external magnetic field. It's going to experience more magnetic field, and it would be more difficult for it to resonate, to go into opposing spin. So it would be very difficult for it to go into opposing spin and a higher resonant frequency. So it's going to have a very high resonant frequency. Vice versa, if there is an electron that's completely surrounding it and shielding it, and the electron cloud is deflecting all the external magnetic fields, ठीक है कि magnetic field आई है और वो it got deflected by the electron. So the proton is not really experiencing a very strong magnetic field, and it's not going to be very strongly aligned. It would be a lot easier for it to go into opposing spin. ठीक है, so that's the other situation. So the point is that the hydrogen proton is not going to have a fixed resonant frequency. That resonant frequency is going to change depending on what it is bonded to. ठीक है, ये बात भी clear है? Is this clear to everyone?
Yes, sir.
Yes.
अच्छा, तो bonding change हो जाएगी और so all these hydrogen protons, they would be very strongly, the resonant frequency is going to be affected by what they are bonded to. So the basic idea is, that's the first thing. When you see a molecule, what you're going to do is, you're going to find the chemical environments. How many different chemical environments are there in the molecule? So for example, if I have a molecule of the same molecule, like the carboxylic acid that I drew earlier. So the first thing is, okay, you're going to find out how many different chemical environments are there in a molecule. So if you look at this molecule, you would notice that this H has a different environment. It's going to have a different, the proton is going to have a different shielding compared to, these two H are exactly identical because they're bonded to the same atom. These H's are also identical since they are bonded to the same atom. So a very, very slight difference in the chemical environment would result in a different resonant frequency. So this is going to resonate at frequency F1, this would resonate at frequency F2, and this would resonate at frequency F3. Okay, even though these two are very similar, but the hydrogen protons are bonded slightly differently. For example, over here, the hydrogen proton are bonded to a carbon, which is bonded to a CH2. Over here, a hydrogen proton is bonded to a carbon, and right next door, there's something else. So even just a very slight difference would result in a difference in the resonant frequency. So आपका जो graph होगा ना absorption का, that's going to look like this, that there's going to be 3 frequencies that are going to be absorbed due to resonance. There's going to be F1, F2, and F3. So that basically tells you that you have these hydrogen protons and there are 3 different chemical environments. And the absorption depends on the number of hydrogen protons. ठीक है, यहाँ पे there is 3 hydrogens in the same environment, so they're going to absorb a lot of frequency. ठीक है, so यहाँ पे absorption rate of F1 would be absorbed 3 times more compared to, let's say, F3. ठीक है, F3 के अंदर there's only 1 hydrogen, और F2 के अंदर ना there are 2 hydrogens. तो उनकी जो relative absorptions होंगी ना, they would be exactly following the same pattern. Okay, the ratio of the absorptions is going to be 3:2:1. So what does the height tell you? The height tells you the number of H
Number of
atoms.
hydrogen atoms.
Yeah, in the same chemical environment. So here's, let's do another molecule. I have so in this case, how many different chemical environments are there in this molecule? Anyone?
Sir, 3 or 4? Sir, 4.
I mean, are these two CH3s exactly the same or not?
Actually, sir, I think they're the same because they're bonded to the same thing.
ठीक है? I mean, they're bonded and the environment completely is the same. ठीक है? It's the same things bonded over here. So just 1 second, azan ho jaye zara.
Sir, I think you're muted.
So I was talking about this one. This one, this CST and this CST are exactly identical. So they're going to resonate at frequency, let's say F1. ठीक है? This H is different from all the others. So it would resonate at frequency F2. And the H over here that is connected to OH, that's different than all the others as well. So let's say that resonates at frequency F3. So if you make a graph taking F1 and F2 and F3 as the frequencies that they're resonating at, it's going to be F1, F2, and F3. So F1 is going to have very high absorptions because there are 6 hydrogens that are absorbing that particular frequency. And F2 and F1, they just have 1 hydrogen, so their absorption is going to be very less in a relative way. Okay, so this is how the Nmr spectrum would look like. So this is one thing that you have to remember. Okay, how many chemical environments there are in the molecule, So the number of frequencies that are going to be absorbed depends on that. And the height measures the number of hydrogens in that particular chemical environment. And then you have a splitting pattern, which is caused by neighboring interference. So there is a thing called a splitting pattern, which is that these peaks are not going to be unique peaks. They're not going to be just single peaks. What's going to happen is that if you have a CH3 molecule and right next door, let's say there's a carbon which has 1H and there's some other things bonded to it, but the carbon next door has one hydrogen atom. What would happen is that this hydrogen proton is going to affect, I mean, let's say this is resonating at frequency F1. Now, this hydrogen proton over here, the neighborhood hydrogen proton, is going to affect uh, or interfere with the resonant frequency of these hydrogens in two ways. One is that it might align with the external magnetic field or it might be opposing the external magnetic field. So it's going to cause interference in two ways, which is why your frequency F1, it's not going to be one unique frequency. Instead, because of this tiny interference caused by the neighborhood hydrogen proton, okay, its magnetic field is going to interfere because remember, this magnetic field is going to change the external magnetic field. Okay, because resonance was happening because of the magnetic fields of the hydrogen protons. This hydrogen proton is going to interfere with their magnetic fields in two ways. So overall, what would happen is that that frequency F1 is not going to be one single frequency. Instead, it's going to be a doublet peak, which means that it would split into two. Both of them would be very close to each other, uh, but you're going to get a doublet peak because of the interference. And this hydrogen proton is going to interfere in two ways. So the frequency F1 is not just going to be one unique frequency, it's actually going to be two frequencies around F1 that would be very close to each other. Similarly, if you have on the neighboring carbon atom, you have two hydrogens, then the number of possible ways in which interference happens, that would increase. Uh, so this hydrogen proton would also interfere with the frequency, resonant frequency of these three hydrogens. And if the neighboring carbon has two hydrogens, there are three ways in which they could interfere. One is that both of them could be pointing in this direction, or both of them could be pointing in opposite direction, or one of them could be aligned and the other one could be opposing. So there are three different scenarios, which is why the frequency F1 would then be split into three different frequencies because of the three ways in which the neighboring hydrogens are interfering with it. So the rule is, and that's known as the N+1 rule, that if the neighboring carbon has N hydrogens, and you have to look at the neighboring carbon only. So it has NH atoms or protons. So the peak would split into N+1 peaks, which basically means if the neighboring carbon, so we can make a table that if the neighboring carbon, it has one hydrogen, so the peak is going to be a doublet peak. If it has two hydrogens, it's going to be a triplet peak, which means it would split into three, like the one shown over here. If it has three hydrogens, it's going to split into a quadruplet peak. There would be four sub peaks, and so on. Beyond four, what you call them is a multiplet. Okay, so if the neighboring carbon has five hydrogens or six hydrogens, then that's going to be a multiplet. And there's the neighboring carbon atom could also have zero hydrogens. If it's zero hydrogens, then there would be no splitting. There would be no interference at all. So So if the neighboring carbon atom has 0 hydrogens, then it's going to be a singlet peak. So I'm going to apply the splitting rule to the molecules that we did. So 6 hydrogens, the 6 hydrogens over here, the neighboring carbon has 1 hydrogen. Okay, so this carbon, this is the neighboring carbon of these hydrogens and this hydrogen as well. So there's 1 hydrogen. So that means this over here would be a doublet peak, it won't be a single unique peak, but it's going to be a doublet peak. What about this H? This H, the neighboring carbon atom has a lot of hydrogens. There are hydrogens on the right side and there are hydrogens on the left side. So this one, F2, is going to be a multiplet peak, which is going to look like this. That there would be lots and lots of tiny subpeaks around F2. There would be a lot of interference caused by the resonance of these hydrogen protons and these hydrogen protons on this frequency. And about the n+1 splitting, remember this, that there would be no splitting for OH and NH2 peaks. And the reason for that is that if you have an OH, then oxygen has these lone pairs. So this hydrogen proton could be aligned or it could be non-opposing. These hydrogen protons could be aligned and they could be opposing as well. Because of the lone pairs and because of the extra shielding, the interference between the magnetic fields over here and the magnetic fields over here would be very minimum, which is why they're not going to interfere with each other and there wouldn't be any interference. So this would be a single peak and this would be also a single unique peak. So remember this, that no splitting because of OH and NH2 peaks. So which is why if we look at this molecule over here, the F3 peak is going to be a unique single peak because there's going to be absolutely no resonance, but no interference. The lone pairs over here would protect this H. So nothing would happen to this H either way. If these are resonating, they're not going to affect this. And we can apply the splitting pattern over here as well. This F1 would split into 3 peaks because the neighborhood has 2 hydrogens. So let's split the F1 peak into a triplet peak. This CH2 peak over here would split into, the neighboring has 3 hydrogens, so it's going to be a quadruplet. And this OH is going to be a single unique peak. It won't be causing any splitting, and it's not going to split itself. Okay, is this clear?
Yes, sir.
Clear? So I'm
Yes,
just
sir.
going to summarize. In the next class, we can start doing questions. I'm just going to summarize this. We still haven't studied D2O, but let me summarize what we studied. One is the concept of resonance, and what you have to remember is the number of chemical environments. You should, by looking at a molecule, you should be able to figure out that there are 3 different chemical environments. Or over here, there are 3 different chemical environments. These two are exactly the same. This is different, and this is different. So the resonant frequency depends on the chemical environment, and the height of height of absorption depends on the number of hydrogens that you have in that particular chemical environment. So if these 3 are absorbing frequency F1, because the greater number of hydrogen protons, frequency F1 is going to be absorbed a lot. This hydrogen would be absorbing frequency F3, but there's only one of them. So the frequency F3 is not going to be absorbed that much. And then you have to remember the splitting pattern, which is K, agar neighborhood mein there are 2 hydrogens, so they're going to interfere with this, and the splitting caused by these 2 hydrogens would be 3, n+1. Iski frequency F2 jo hogi, that would, the neighboring carbon atom has 3 hydrogens, so it's going to split into 4 peaks. OH is not going to split, NH2 is not going to split as well. Okay, ye clear hai? So we'll continue with this and then we'll do questions once we are done with this. Mainly we are done with this. बस थोड़ा सा मैंने एक वो एंड में D2O और TMS का ना बस थोड़ा सा बताना है, but otherwise we're almost done with NMR. We'll do questions in the next class. ठीक है?
ठीक है सर.
चले, okay, take care.
Hafiz.